All right, so let's carry on. I'm very excited to talk about quantum gases, or sorry. So the first quantum gas that we'll talk about is the photon gas. We'll actually work out the blackbody radiation. But before we do that, let's do a case which is a lot more very like a little bit of a simpler case. Can you just hang on 1 second? I'll be back. I'm sorry about that. People in Bangladesh are just so unprofessional. I'm just amazed. Like the air conditioner guy just showed up with the air conditioner without letting me know, assuming that I'd be free. I mean, this is crazy. Anyway, the class will go on. So yeah, let's start the quantum gases thing. Sorry, these are the kind of problems you have when you're working from home. So let's first deal with the simpler case where we have a bunch of particles in a box, okay? So we want to figure out something about the particle in a box. So we have a box which is of length L on each sides, okay? And we have a bunch of non-interacting particles, okay? So what we want to find out is, what are the density of states? Meaning that, for example, when we are doing when we're writing down the density matrix, we will have to do something where there'll be an integral over d of E. But what we want to find out is that, given a certain interval d of E, what is the density of states there? And then there will be integrand here, okay? So we want to figure this out. So to do that, the first thing what we want to do is that we want to describe each particle's its wave function. So its wave function is given by, so it's essentially a particle which is free to move, but it cannot go outside the box. So we are going to say that okay, can you just hang on 1 second? I'm gonna give a piece of my mind to these people. I'm really sorry about that. Sorry, I told them to come back later. All right, so this is the wave function. And the idea here is, sorry, can you all hear me now?
Yes, sir.
Yes,
yeah,
sir.
I'm very sorry about the interruption. I told them to come back. So yeah. So the idea is that, our the wave function is that of a particle which is free to move around, but it cannot go out of the box. So the wave function has to be actually in reality of the form where it goes to 0 at the boundary of the box, right? So it can be either cosine or it can actually be, depending on how you choose your coordinate system, it has to be a cosine or a sine function. But we would just want to make life a little bit more simple, so we just do the exponential, which has a real part cosine and an imaginary part sine. And we don't want to bother about whether choosing sine or cosine. So what we do is that we just choose a periodic boundary condition so that both cosine and sine they work out. But of course, this has the length L. Because it has the length L, this case cannot be arbitrary. One of the things about a wave function is that a wave function cannot be multi-valued. So when I go from x to x plus L, this wave function must come back to the same thing. Now, for that to happen, k has to be quantized. So the ki has to be 2 pi ni over L. Okay? Is that clear why this is so? Because if you ni is an integer, if you have 2 pi n over L and you multiply that by L, which is what this term is, then that will cancel out, and this is 2 pi times an integer, and therefore e to the power minus I 2 pi ni is going to be a 1. Okay? And therefore it will be single valued.
So this says the periodicity should be reserved here.
Yeah, the periodicity is what is guaranteeing that this thing is a single valued function. Okay?
So one input doesn't have two outputs, something like that?
Exactly, yeah. Because, if the wave function is multi-valued, then of course it won't have a physical interpretation, right? Because then, what wave function are you going to use to predict the probability, right? Because you have to take the square of the wave function and all that, right? So therefore, the wave function always has to be single valued. That's one of the requirements of quantum mechanics. So basically what we are saying is that the momentums are now quantized because this is nothing but proportional to the momentum, right? Because if you take the derivative, and then what is the energy of the particle? There is the potential energy, is just p squared by 2m, right? There's just kinetic energy, right? So that applied on my wave function is going to give me minus h squared by 2m. This is the gradient. This is the del squared operator. And then, this thing is for normalization. I won't go into that. And this is going to be minus v e to the power minus I k dot x. And, if I now apply the Laplacian on this, what I get is h squared k squared by 2m psi, right? So this is not, so k squared is going to be a function of these integers and I. So therefore, so this is nothing but the energy, because this is the energy operator. This is essentially what we're doing is h, the Hamiltonian acting on psi, giving me E of psi. That's exactly what this equation is. So what is E? E is going to be E is a function of the 3 integer n. So this is a vector. So this is going to be h squared by 2m 4 pi squared by L squared nx squared plus ny squared plus nz squared. Okay? In other words, this is going to be 4 pi squared h squared 2ml squared, the vector n squared. Okay? Is that clear?
Not quite, sir.
What is not clear about this?
How was the I mean,
okay, let me go back. So I mean, at least this should be clear, right? How you just apply this operator on this thing and you get
yes.
right. So but we saw that k has to be quantized. Kx, ky, kz has to have that form, right? So all we're doing is putting that in there and then identifying this number as E, because this equation is nothing but the eigenvalue equation, right?
Oh yeah, got it.
Yeah. And then if you now label E by the integer, this is what you get, okay? All right, so now the thing is that, so our partition function formally is going to be something like Z is going to be sum over all the possible integers. It's a 3 tuple of integers, right? Positive integers. And none of the integers, like the integers cannot all be 0, right? Because then we don't have a wave function. And then it'll be e to the power minus beta en, right? So this is going to be our partition function. Now the thing is that, you know, this sum is kind of like hard to do, and you know, we are working in a regime where the length of our box, the dimension of our box, is much greater than, say, the thermal wavelength, the thermal de Broglie wavelength, right? So so in this regime, what we can do is that, remember that the de Broglie wavelength was something like 2 pi h squared divided by m kBt. So we are also assuming that T is quite large, like T is much greater than 0. Okay, so a room temperature or something like that, right? So if that is the case, then the de Broglie wavelength is very small. And of course, you know, h squared is also very small. So therefore, you know, we can just like take L to be much larger than lambda, okay? So, you know, having done that, we can then say that, okay, we can approximate this summation over n by an integral over d cubed of n, okay? And now if I change my variable from n to k, I get L cubed by 2 pi cubed d cubed k, okay? Now what is L cubed? L cubed is nothing but v. And assuming that our integrand is going to be, you know, it only depends on the modulus of k, we can do the angular integral and get 4 pi out, and then I'll get 2 pi cubed, and then here I will have integral from 0 to infinity, and then there would be the modulus of k squared, the integral over the modulus, right? And the other thing is that we can also approximate the energy. Well, the energy is equal to, the energy is equal to h squared k squared by 2m. So the idea here is that, you know, we we are treating the momentum variable k, or it's more appropriately the wave number variable, because momentum is related to k by h bar of k. We are treating that as a continuous variable, okay? And because the approximation we are making is that lambda is much smaller than the dimension of the box, okay? So if I do that, then well, from here we get d of e is going to be h bar squared 2 times k of dk divided by 2m, okay? So what we get is that from here, we are going to get 4 pi v by 2 pi cubed integral from 0 to infinity dk k squared. And then we can express that in terms of an energy over integral over energy, and g of e, and then g of e is going to be v by 4 pi squared 2m h bar squared 3/2 square root of e, okay? And this is known as this is the density of states, okay? For this sort of particle, for a non-relativistic particle in a box. Okay, so how the number of states change as a function of the energy, that is the density of states. Okay? Is this clear how we got from here to here? So just to repeat, this is how we got from dk to de, and this is how we got from k to e, okay? And here we had, say, k squared. So k squared gave us a factor of e, and then dk gave us a factor of de by k, but yeah, and so k is square root of e, so there was a factor of e before, and divided by square root of e, that's how we get a factor of square root of e, okay? Okay, any questions?
Sir, how did the 4 pi v by 2 pi cube dk k square become de
Oh, this
ge?
is just, this is 4, this is 8. So you get a factor of 2 here, and pi cubed, so you get pi squared, and this 2 came from this 2. I think, yeah. Yeah, I mean, you can just and this, yeah. Yeah, just work this out. This should work out. Okay. I mean, the factor of pi and 4, those are not critical right now, because those are order one numbers. What's critical are v, m, h bar. Those are the critical things. Okay.
No, sir. I mean, how does the integration of de ge come from the previous?
That's, we are just changing variables in the integration from k to e.
Okay, got it.
Yeah. Okay. All right. So now you can do the same thing for a relativistic gas, and for photon, we'll need to treat the relativistic gas. Okay. So for relativistic gas, what we do is that we just use the relativistic energy momentum relationship. So E is no longer just p squared by 2m, but E will be given by p squared c squared plus m squared C4 square root. Okay, and if I use the de Broglie relationship, this is going to be h squared k squared, and I think there's a c squared that I missed in my lecture notes, m squared C4. Okay, so this is the relativistic gas, and now if you do the same thing again, then you get G of E as VE. You get a different result. 2 pi squared H cubed C cubed square root of E squared minus M squared C4. Okay? And for photons, M is going to be 0. So for photons, this will be VE by 2 pi squared H cubed C cubed times E, which gives me E squared here. But photons will have 2 polarizations, so there will be a factor of 2 here. And that 2 will cancel this 2. Okay, so this is the result for photon. All right?
Sir, if the box wasn't so large from the de Broglie wavelength, would the particle get out of the box?
No, you're assuming that the box is impenetrable. That's an assumption you're making. So it's it wouldn't get out. But if the box wasn't large enough, then you could not do this approximation, and therefore you'd actually have to do the sum explicitly. Okay.
So what is the point of getting these G of E's? What are we working towards?
We are working towards figuring out, say, what, so, okay, so the idea is something like this. We want to do this integral, right? Something of this form. So suppose we are working out what the energy, radiant energy is, what the average energy is, right? So we want to do something like sum over the energies, possible energies, and e to the power minus b of En, right? So now the thing is that what is this thing? This is what this measure is. Okay, this is basically is being given by this. When we are summing over all the states, we have to have the right measure. We have to have the right density, right? Because you're summing over some, you cannot just say, oh, this is just d of E, right? In quantum mechanics, the states may be placed in a way that is, there has to you have to multiply by, how dense that state is. Okay.
So kind of like a weighted sum.
Yeah, the distribution of states in that energy, right?
I see.
So that's basically what we're figuring out. This sum, what happens to the sum in the continuum limit?